Today I'm going to talk about finitely generated free modules over some base ring R, which I assume to be a commutative associative running with unit. And I say that an R module M is finite if it is finitely generated. So I do not necessarily assume that M is finite as a set. For free modules, it means that a finite module has a finite basis. So if M is a finite free module, then it has a finite basis. Finite basis set. And for these kinds of modules, I would like to reformulate the definitions of linear independence and generation. I will use the following fact. If I consider the set of homomorphisms from R taken n times to m, then you are now proving in your current problem set that this is isomorphic as R modules to homomorphisms from R to m tuples of those. And a homomorphism from R to m is defined by the image of 1, so this is in turn isomorphic to m taken n times. So a homomorphism phi from Rm to m is given by the same data as an n tuple of elements of m. So I take phi of the first standard basis vector, 1, 0, 0, 0, etc. through phi of the nth standard basis vector, 0, 0, 0 through 1, and I denote this tuple by A. So in this language, let me fix an R module, and A will be a finite ordered set or tuple of elements of M, that is, A is of the form M1 through Mn. Then I say that A is linearly independent if the corresponding homomorphism from R n to m is an injection. So I formulated as a definition, but I want to show that this definition coincides with the one I gave on the previous lecture. So for this, let me describe explicitly how phi sub a looks like via this correspondence. If a is of this form, then phi a of the first standard basis vector 1, 0, 0, 0, etc., which I denoted here by E1, is equal to M1. Phi a of the second standard basis vector, I set it to M2, etc., through phi a of the nth standard basis vector, 0, 0, 0 through 1. I take it to be equal to Mn. So if I have some arbitrary tuple of scalars from R, C1 through Cn, in this Rn module, then phi a applied to this tuple will be C1 M1 plus C2 M2 plus etc. Cn Mn. And saying that phi a is an injection is the same as saying that the right hand side is equal to 0 precisely when all the coefficients are equal to 0. So phi a of C1 through Cn is equal to 0 if and only if all the coefficients are equal to 0 because of injectivity. And this means that this set is linearly independent. And conversely, if A is linearly independent, then assume that there is some element in the kernel of phi A. Then we get that this linear combination represents 0. And by linear independence, we get that all Ci's should be equal to 0. And so we get that phi A is an injection. In a similar fashion, I can formulate when A is a generating set for M. And I say that A generates M if the corresponding map by I from Rn to M is a surjection. And again, I want to prove that it coincides with the previous definition. So again, if A generates M according to the previous definition, It means that any element x of M can be written somehow as C1 M1 plus C2 M2 etc. plus Cn Mn, so this is equal to x. But this part is precisely where phi A sends the n tuple of Ci's, so x belongs to the image. And conversely, if Rn is surjective, if phi A is surjective from Rn to M, then we can write any element x as an image of this tuple under phi A, which means that x is representable as a linear combination of mi's. And then A is a basis for M if the corresponding homomorphism phi A from Rn to M is an isomorphism. So we have just proved that all free finitely generated, or in our new terminology, finite free, R modules are isomorphic to R, to the direct sum of R with itself for some n. And because I have just given a new formulation of the notions of generation and linear independence, I want to consider a simple example to see explicitly what this isomorphism does. So for the base ring R, I take the ring of integers, and for a module, I take the free Z module of rank 1, which is Z. Then I can take A equal to the set consisting of just 2. And in this case, phi A goes from Z to Z because we only have one element, so here we take Z to the first power, and phi A of an element n is equal to 2n. And so we can see that this map is injective. So A is linearly independent. But it is not surjective because we don't have 1 in the image. So 1 does not belong to the image of phi A. So A is not a basis. Then I can take two elements 2, 3, and then phi a would now go from z2 to z, because we have two elements here, so we take z to the power 2, and phi a of n1 n2 is equal to 2n1 plus 3n2. And we can show that phi a is surjective, because phi a of -1, 1 is equal to 1. So by multiplying by any integer, we can get any integer in the image. So this lies in the image of phi a. So phi a is surjective. So it generates, so a generates z. But phi a of -3, 2 is equal to 0, and it is a non-trivial element in the kernel of phi a. So a is not linearly independent. So a is not a basis again. And a basis here would be the element consisting of just 1. Phi a goes from z to z, and phi a of n is equal to n times 1, which is n. And so phi a is an isomorphism, and it means that a is a basis. And since we have one element in the basis, we say that rank of z as a z module is equal to 1. And we know for vector spaces that rank is well defined, so if we have a one-dimensional vector space, we won't be able to find a basis consisting of two elements. And we can prove that for commutative rings, free modules over them also have well-defined rank. However, this is not true over non-commutative rings, so we will be using commutativity. So now I'm going to prove this claim that rank of a finite free module is well defined. So theorem, let R be a commutative ring associative and with unit, and assume that a free module of rank n is isomorphic to a free module of rank m. Then n is equal to m. Let me start with a construction that I will use in the proof. Let's say M is an R module and I is an ideal inside R. Then define the submodule IM as the set of all combinations of the form xi mi, where xi is in the ideal and mi is from the module. So it is a submodule of M because any finite sum of elements of this form, when you add another element of this form, we get another finite sum. And if we multiply any element of this form by an element of the ring, or times the sum of xi mi, then I can use distributivity to multiply every summand by r. And by commutativity, I get that I can write it as xi times r mi. And so xi is still in the ideal, and r mi is in the module M. And so we again got an expression of this form, sum of linear combination of elements of M with coefficients in I. And in particular, if M is a free module, R M, then IM, I can write it as tuples of coefficients in I, because I have I times Rm. So since Rm is generated by the standard basis vectors, then I times those standard basis vectors would generate Im. So I can write it as IRM. So I can write this submodule of a free module with coefficients in I as m tuples of elements from the ideal I. Now I want to prove the following lemma. If we have an R module M and an ideal in R, then M quotient out by IM carries a natural structure of an R mod I module. Let me prove this lemma. I define the R mod I module structure. So I take an element represented by R in the quotient ring and an element represented by M in the quotient module, and I send it to the element represented by Rm here. And so if this is well defined, this defines the structure of a module because we assume that M is an R module, and so the axioms of the module would naturally follow from this formula. So it remains to show that this is well defined, which means that this definition does not depend on whether I choose another element from another representative from the equivalence class. So let me see where R plus x goes, where x is from the ideal. How this element acts on M. I get that this is defined as R plus X M. And by distributivity in the axioms for modules, I get that this is equal to Rm plus Xm. And because quotient modules are well defined, by their definition of addition, I get that this element is equal to the class represented by Rm plus the class represented by Xm. But Xm is an element of the submodule Im, so it represents the zero equivalence class, so I get that this is equal to Rm. And so if I choose another element, another representative from the equivalence class of R, I will still get the same result, Rm. And now I'm well equipped to prove the theorem. So I want to apply this construction to both of these modules. And for ideal, I take I equal to some maximal ideal of R. Then, since these two modules are isomorphic, we have that Rn mod M Rn is also isomorphic to Rm mod M Rm. But I showed that I showed that I times Rm is naturally the m tuples of elements of the ideal, so I can write it as Rm mod out by m taken m times, and so the left hand side is also Rn mod m to the nth power. And modding out n tuples of numbers by n tuples of elements of the ideal is the same as modding out each coordinate separately. So I get that this is isomorphic to R mod m taken to the power n, and this is R mod m taken to the power m. And now use the lemma to conclude that both sides are R mod m modules. But since M is a maximal ideal, the quotient is a field. So, in fact, both sides are vector spaces. And we see that the left-hand side is an n-dimensional vector space, and the right-hand side is an m-dimensional vector space. So the dimensions should be equal because we are now working over a field where the notion of dimension is well defined. So n should be equal to m, just as we wanted. And since we observed a little while ago that every finite free module is isomorphic to Rn, we have just proved that if a finite free module is isomorphic to Rn and Rm, then n is equal to m. That is the rank. The notion of rank is well defined. And now I want to describe a convenient way of writing homomorphisms between free modules. This is the familiar notion of matrices, except here we get more abstract coefficients. Namely, we have coefficients from the ring R. So R, we again take some commutative ring. So let's say that we have the group of homomorphisms between two free modules, Rn and Rl. Then you are showing in your p-set that we can take direct sum, finite direct sums out of this home R notation. So we get that this is isomorphic to home R from R to RL taken n times. And again, because homomorphisms out of R are defined by the image of a unit element, or like by the image of 1, we can write that this part is isomorphic to RL naturally, so we get RL taken n times. And we denote this, so this is isomorphic to R to the power Ln. But instead of just writing these long tuples, we will organize them into a table called a matrix. And we denote this set by mat matrices with L rows and N columns. So the convention for writing matrices is taken from linear algebra. Let's say that E1 through En is the standard basis for Rn. So E1 is this tuple 1, 0, 0, 0, etc. Then, if I have phi from Rm to Rl, then the corresponding matrix I write it by columns, and the first column will be the coordinates for the image of E1, the second column will be the coordinates for the image of E2, etc. And I denote the matrix entries as A with subscripts and superscripts. So this first row and first column is A11. Then first row, first column, second row is A21, etc. through AL1. So because the image is of rank L, etc. And I get here A1n through ALn. The rules of matrix multiplication correspond to composition. So let's say that we have now three modules Rn, Rm, and Rl with the homomorphisms phi and psi, whose corresponding matrices are A and B. And let's say, for the sake of the argument, that the standard basis in Rn is E1 through En. The standard basis in Rm is F1 through Fm. And the standard basis in RL is G1 through GL. Then I want to find matrix entries of BA, the matrix corresponding to the composition of psi phi. So let's take, for example, the matrix entry in the first row and first column, BA11. And again, we are writing this product matrix in such a way that the first column corresponds to the coordinates of the image of E1. So this is psi phi of E1. Okay. So let us compute what psi phi of E1 is. It is equal to psi applied to, and we recall how the matrix A looks like. So we take this to be the coefficients of the standard basis in Rn. And this will be the image of E1 under phi. So this is the matrix corresponding to phi. So we have that this is A11 F1 plus A21 F2 plus etc. M1 Fm. So I write it with sigma notation as A I1 Fi, where I ranges from 1 to the rank of Rm, which is M. Because psi is a homomorphism, I can move the sum outside. So sum and the coefficient ai1 times psi of fi. And now fi, the image of fi goes to the linear combination of gi's, or gi's with the coefficients that are in the ith column of B. So imagining that this is B, we would take the ith column of this matrix and take its coefficients to write them by G1 through GL. So we have some I from 1 to M, AI1, and then we have times B1I, G1, plus etc. B L I GL. And so again I can write it in sigma notation and I get sum of I from 1 to M, sum of J from 1 to L, A I1 times B J I times Gj. For those of you who have seen Einstein's index notation, I chose the positions of the indices in such a way that when I sum, the index which I sum over appears on the top and on the bottom. And sometimes people just don't write this part with the summation because they remember or understand that when you have repeating indices on the top of one matrix and on the bottom of another matrix, then you sum over those indices. Anyway, we can extract our coefficient BA11 from here by taking the coefficient in front of G1. So BA11 is the sum over I and j, pairing over their respective ranges of A1I times BI, and here I take j equal to 1, so I get B1I here. And so if we write B and A as matrices, that B11, B21, etc. through BL1, B12 through B1M, B22, BLM, times the matrix A, M1, AMN. Then the product matrix, its first coefficient BA11 will be equal to the sum of B1I, so all of these coefficients, multiplied by AI1, so all of these, and sum them up to get BA11. So we recover the usual rule of matrix multiplication. We take row and multiply it element-wise by the column. And note that here we have the same number of entries in both the row and the column. And so we multiply them element-wise and then sum it over to get the scalar, which is the entry in the product matrix. Here it should be I from 1 to m, because we eliminated j already.